last lecture on heat and temperature. I'll kind of go over a little bit about your next test. That is on May 4th. It's a little bit away, but it's, I guess, never too early to start on that. So let's do that. Okay, so you're going to have approximately 13 questions. I say approximately, maybe plus or minus one. I might change a few things before then. This test will be entirely on Blackboard. So, yeah, it's not letting me write. It was earlier. I wonder why it stopped. Give me a second. Discard. Open with other external. There. Okay, so, yeah, it's going to be entirely through Blackboard. And since it's your first test, I'm doing it through Blackboard. I'm going to give you 150 minutes. It's 2.5 hours. It's more than enough time to do it. Because I'm basically on new territory. Never done that before. That being said, it will be multiple choice. I have not figured out a way of seeing your work at the moment, so I'm probably going to make it worth less points than the other tests. Normally I do 70, 70, 70, and I drop your lowest test score. I guess in order to be fair, I'm going to have to make it worth less points unless I come up with something in the next 2 weeks before that test comes out. Like your previous test, it will be open notes. And what do you expect to see? You will see one thermal expansion question. So that's basically like where you have, let's say, alcohol, which if you recall is 1% per 10 degrees Celsius, and then you need to change that to a decimal, so it's 0.01 per 10 degrees Celsius. And then if you have like a 40 degrees Celsius change, then the decimal change is 0.04. What that means, remember, is that 0.04, let's say your original volume was 100, that's going to give you, what is that, I'm having a brain fart here. It should be simple. For some reason, yeah, 4. For some reason I wanted to say 0.4 in my head, so I needed to calculate it. 4 milliliter change. So it could, basically, if you're heating it up, it'd be 4 milliliters above, and if you're cooling it down, it'd be 4 milliliters below 100. That for that problem. You'll have some graph interpretation problems. 6 thermal energy. Thermal energy is the MC delta T is equal to your change in energy. And then 2 concept questions. These will mostly come from the lectures. If you watch the lectures, I should have talked about it, and you should be able to answer them. So, one other thing I wanted to point out is, can't remember, so I'll come back to it if I remember what I wanted to point out. But I think that's, I guess, all I was going to say. I feel like there's one more thing, but if so, I'll come back up and say it. I will do a couple of review problems of what you might see on the test. I totally remember what I was going to say earlier. There is a posted study guide. I highly encourage you to do study guide. Forgot to put that up there. So, if you do the study guide, it will help you pretty decently on the test. Okay, 15 grams of ice is heated from -50 to 150 degrees Celsius. How much energy does the process take if the specific heat of ice is 2.1 and the specific heat of steam is 2.0 joules per gram degree Celsius? Okay, so basically I need to find a lot of different energies. First, I need to find the energy it needs to take as ice from -50 to 0. What happens at 0? It goes through a phase change. Once it goes through a phase change, I need to account for that energy. And that's the energy that I need to change it from a solid to a liquid. And remember, it's latent heat of fusion, which means that the temperature of the ice does not change until it all changes over. At that point, it is now a liquid, and we will need to heat it up from 0 to 100. Because after all, under STP conditions, your liquid water cannot be water cannot be a liquid below 0 degrees or above 100 under SDP, and that's what we're dealing with. Once you get to 100, as I just mentioned, phase change. So we need to go from a liquid to a gas. And then once it changes over to steam, we're going to heat that up again as a gas from 100 to 150. So all these different energies I need to account for. So my easiest way is to write out the formulas. This will be M, and I'll say Ci for C of ice, delta T of I for ice, then the latent heat of fusion, which times the mass, which will be MLF, plus, once it changes over to a liquid, we need to heat it from 0 to 100, so that'll be MCL, delta TL, L for liquid, hits 100, changes to steam. That's going to be MLV for the latent heat of vaporization. And then finally, as steam, we take it as MCG for gas, delta GG for gas. Notice that the M is common throughout, so I can pull that out. It's going to make my calculations a hair bit easier. That gives me Ci delta Ti plus LF plus Cl delta TL plus LV plus CG delta TG. Now I plug in my numbers. Okay, so this is, I'm going to move over as far as I can. Well, I guess that's as far as I can. 15 grams. Okay, C of ice is going to be 2.1. So I'll take 2.1 joules per gram degrees Celsius, and I multiply that by 50, plus 334 joules per gram, which is the energy needed to change it over from a solid to a liquid, plus 4.18 joules per gram degrees Celsius times 100, plus 2258, which is the energy we need to change it to a gas. And then finally, 2 is for steam, so 2 joules per gram degrees Celsius. Oopsie. Gram degrees Celsius. And then times that by, 50 degrees was the change of temperature as a gas. Closing off. So, notice a couple things. Your Celsius goes away right here and right here, and that leaves you with joules per gram throughout, but there's a gram outside of that, so that's going to end up giving you a joule answer, which is kind of what we're looking for in this case. So, putting in my calculator real fast, 2.1 times 50 plus 334 plus 4.18 times 100 plus 2258 plus 2 times 50, multiply that by 15, I get around 48,225. Alright, so the energy, 48,225 joules. Okay. So that's the energy needed. So if you have a problem like this, you have to account for all the different energies. If it says ice, it will have a separate specific heat, and you need to account for that energy. If it says a gas, it will have another specific heat, and you need to account for that energy. Next problem, we have 100 grams of ice, negative 40 degrees Celsius, and it's mixed with ethanol at 20 degrees Celsius. It comes to a final temperature of negative 10. What's the mass of ethanol? So, different formulas you can use, but we basically use the regular conservation of energy, which is M1C1 delta T, let's do it, TF minus TI1, and that's equal to negative M2C2 TF minus TI2. Remember, the energy gained by one is the energy lost by the other. Okay. Anyways, so what I need to do is solve for the mass. I have the information, so I just plug in what I know. Alright, well this will be 100 grams with the mass of ice. Its specific heat is 2.1 that we learned from the last problem. And the final temperature is going to be a negative 10, so it'll be negative 10 minus a negative 40. So finest minus initial. And then closing that, negative M2, we don't know. And I forgot my negative as I said that. Specific heat is 2.4 joules per gram degree Celsius. And then final temperature is going to be negative 10 minus a positive 20. Closing there. Okay, so you just need to solve for M2, and then you plug that into your calculator. So that's 100 times 2.1 times, looks like 30. Then divide that by 2.4, and then divide that by, well, more or less 30. And you get 87.5. So the M2 is equal to 87.5 grams. I believe you do have one problem like this where you're going to have to solve for either a mass or a specific heat, and you basically just use the fact that it's the conservation of energy, which is that the energy gained by one is equal to the opposite of the energy gained by the second one. So, all right, let's do one final one. You will have one like this. You had two already in the labs, or you're going to have two. One with latent heat of fusion and one with latent heat of vaporization, but here goes. We have 100 grams of ice at 0, so it's at its melting point, dropped into 150 grams of coffee at 80 degrees Celsius. What will the final temperature of the iced but melted coffee, meaning we're assuming it's not iced coffee because it melted, treat coffee as if it's water. So, all right. Well, what do I know here? I know that the change in energy that goes into changing ice from a solid to a liquid is going to go into cooling the coffee. And that is my first step, is to figure out, well, what's the change of temperature of the coffee. I generally am not going to use negatives or positives. I think it's easier just to think about it logically. And so that's what I'm going to do. So I take, okay, that's going to be M, and since it's ice, it's going to be LF, and I need to put MI for ice, and then that's going to be MC for coffee, C, that's a really bad idea, coffee, Java, MJ for coffee for Java, C, and then delta T. So, I want to figure out what delta T is. So I'm going to take my mass of my ice, which is 100 grams. There are 334 joules per gram. Catch. And then I divide that by my mass of my coffee, which is 150 grams, by its specific heat, 4.18 joules per gram degree Celsius. Okay, so 100 times 334, and then I simply divide that by 150 times 4.18. Hang on just a second. Nah, because I totally didn't do that right. Otherwise, I did not get 1,000. There we go. 53.3. Yes, everyone hears you, Cat. Okay. Yep, we still hear you. 53.3. And we're still hearing you. Okay. 53.3 degrees Celsius. So that's my change in temperature of the coffee. Now, I kind of had you do that in the lab. Just say, okay, this is the change in temperature of the coffee. That means that the TI of the coffee is now going to be 80 minus 53.3 to be 26.7 degrees Celsius. And so that's for my coffee. Well, too many C's here. I'll just write out coffee. And then my Ti for ice, that is now water, is going to be 0. So I need to use the TF equation, which, if you recall, is TF is equal to M1C1 Ti1 plus M2C2 Ti2. Use my little cool tool, I figure it out, and then undo my cool tool. And then divided by the heat capacities, M1C1 plus M2C2. So I just plug in what I know. By the way, this equation is nothing more, and I probably said this again, but I'll say it a million times. It's nothing more than this equation. It's just a conservation of energy solved for TF. So, all right, M1, we'll choose that to be ice. Now, since the initial temperature of ice is 0, I can just put a big fat 0 and I call it good. Woohoo! That was easy. Okay, M2, that's going to be my coffee. That's 150 grams. It is 4.18 because we're treating it as water. And its initial temperature is 26.7 degrees Celsius. Use my cool tool. Undo my cool tool. Divided by the heat capacity, so that's going to be 100 times 4.18 joules per gram degrees Celsius. And there's one other thing I need to do here. Plus 150 times 4.18 joules per gram degrees Celsius. Since they're both actually water, I can actually cancel the 4.18 throughout the whole thing because both substances in this case are water. So that makes my life a little bit easier. So let's just be 150 times 26.7, and then I divide that by 250, and I get roughly 16. Okay, so basically you will have a problem like this where you're going to have to either find the energy needed to condense or evaporate steam or freeze or melt water, and then that's going to be in some other substance that you can then figure out the final temperature for. It's always going to be a two-step process. You got to first find the energy needed to melt or evaporate or whatever the substance, and then use the final temperature equation to get that. There are so many different variations I could do on this. I choose just to do this because it's just mathematically a little bit easier. So, all right, that is it. If you have any other questions, please email me.